It is a common opinion that the future will see an expansion of crafts and traffic, given the strategic value of the sea in terms of food and mineral resources and the importance of maritime routes. Of course, there is also a need to keep all of this safe. The control of the seas in the future will be as important as the control of the sky has been until now. It will take place through a wide network of dual-use sensors, carriers and payloads, mainly resident on the seabed. Being in control of the subsea environment means being able to manage this network and interface its components. As we get even closer, we see individual objects that now exist and are in the process of being developed, as you will see later in this presentation. Here you see ROVs, unmanned sonar vehicles, and sonar and subsea charging stations, technology already existing in our industry. Subsea, you find sensors placed on the seabed and processing information as you would find with a network of space satellites. You see charging stations for the recharging of resident vectors that carry their cargo either autonomously or wire-guided. The payload represents the specific asset which is deployed to perform the assigned missions. Such a network will transport the highest variety of payload for defense and civilian applications. The complexity of managing the system on a global level therefore requires the identification of methods that ensure interoperability. The DRAS Modular Submarine Rescue System is designed with an architecture which is tailored to indicate a possible approach. A carrier is any object capable of performing transportation at surface level or above. It can be a ship, a surfacing submarine, or even an aircraft equipped with launch and recovery systems. A vector instead carries the payload subsea, and in general the distinction will be between autonomous and wire-guided vehicles. The payload in this case is a submersible rescue capsule, but can also be a set of autonomous vehicles or an array of passive sonars, or even a microplastic sampling system or a pollution detection device. All of these connect with the same interface to the vector. Using as an example the interface between vector and payload, we can see that it is like a giant USB cable of the abyss, which serves to connect every device. The interface must ensure mechanical standards to connect objects of increasing weight and dimension, cater for different electrical voltage, and support subsea communication systems depending on the distance and amount of data transmitted. The proposed strategy is to pursue this approach in a systematic way. If we draw a hypothetical platform of the emerging subsea technologies and knowledge, currently a bottom-up approach is followed to pursue their exploration. In fact, it could not be otherwise, because we have a fractioned industry supporting entities that manifest their requirement in a similarly dispersed way. This is what we can expect in the initial days of a new era. Process where the various entities cited execute their respective projects. Different research, contract and collaboration tools are used. However, it deals with the knowledge platform in a way that creates overlaps and unattended areas. One of the consequences is that in the future we will not optimize interoperability. In addition, resources are not efficiently utilized and priorities are not easily identified. Instead, imagine that we can cooperate to define a top-down approach or apply the interface we presented above as a general criterion. So we should plan ahead for the implementation of the knowledge platform. This table has rows of technological elements encoded in a list. For example, launching systems, battery management systems, and communication systems. These solutions are connected to each other with standard interfaces that ensure compatibility. That is, each element has a default standard interface that communicates with adjacent elements. The columns represent specific projects, and these are defined as a selection of elements needed to complete each project. Each project requires that its black cells be completed. When a row is entirely or partially blacked out, this means that a technological element is completed, and any completed research can serve more than one column and therefore benefit more than one project. This optimizes the effectiveness of our actions, taking into account the limited resources we have at our disposal. For example, in the field of subsea communication, an optical system based on light coders can be useful in many projects. If everyone interfaces with the same data input and receiving system, the system is automatically compatible. This model could enable the Defence Administration or large corporations to make more effective use of small and medium enterprises, with significantly lower management and coordination expenses for both parties.